the cross-sectional dimensions of the beam, I'm going to label it in the following manner. So, if this is my x-axis along the fiber, this is my x-axis along the length of the fiber, and my vertical axis is y. What's the direction of my z-axis? Right hand rule. Fingers of my right hand align with the x-axis. My palm is now going to face the y-axis. The direction of my thumb is the z direction, right? Like you do in dynamics or statics. Whenever you are taught about three-dimensional axes, so this is the z-axis coming out of the page. The cross section, for the time being, let us assume a very simple cross section. I'm going to say that the cross section is a rectangle. Okay, just for the sake of simplicity, it can be anything. Right? The cross section is a rectangle. The centroid of the cross section will always be labeled as C. So C, centroid of the cross section, and the dimensions of the cross section will be the thickness along the vertical direction and the width along the z direction. So this will be W. And this will be T. Okay, this is just for simplicity. I am looking at a rectangular cross section. Okay, so this is the cross section. If I draw the axes on the cross section, what are the axes going to be? Somebody help me out. Centroid of the cross section. What's the vertical axis going to be for the cross section? Is it the y-axis, x-axis, or the z-axis? The y-axis. What's the horizontal axis for the cross section? Beautiful, Z. Why is that? It's because I'm taking this beam, which you're looking along the front view, and I'm rotating it so that you're seeing only the cross section. So if I'm rotating it, this z-axis, which is out of the page, is now going to be facing to my right. Okay, so that's my axes here. And these axes, since they are drawn at the centroid, are called as the centroidal axes. Okay, they are very important, as you'll see in a minute. Okay, so what I'm going to do is I'm going to cut this beam at two locations and then apply some kind of a load on it. I'm going to take the piece, look at it before deformation and after deformation. Okay, so here is before deformation. I'm going to label 3 line segments which are initially horizontal. AA, that is line segment AA. Then this is BB. CC. Okay. I'm going to take this piece and apply a bending moment on both sides. Let's assume that the magnitude of the moment is the same on both sides. So here is what is going to happen. After I apply the bending moment, in the positive sense, the beam is going to be concave upwards. Okay, so this is the beam. It was initially as I had drawn there, now it has become the way I have drawn it. And there are certain things that you want to think of. The first thing is you want to imagine how this bending process is taking place by thinking of the beam as wrapped around a very large imaginary cylinder. Okay, so I'm going to draw a cylinder, a circle essentially. Okay, so this is just some kind of an imaginary circle. I'm taking the beam, which was right here, and this figure is imagined as if the beam is wrapped around this circular cylinder. Okay, so here is the center. Okay, so this is an imaginary cylinder. And this is called as a cylinder of bending. Okay? And here are the things that one can glean from. So first of all, I'm going to remark those points labeled as A, A, B, B, and C, C in the following manner. A, B, B, and C, C. Okay, so this is the figure after the load has been applied or the bending moment has been applied. The following observations can be made, and I'm going to write them down one by one. First things first, the thickness of the beam does not change. Okay, so this is experimentally determined, and then we develop the theory for it. The thickness remains the same. Okay, so this is still the thickness. As before, this is drawn exaggerated. Okay, so this is not typically how you would see in real life. When a bending moment is applied on a beam, you can't see it like so curved, but this is an exaggeration which will help us understand things. The second observation is that lines that were originally vertical are now rotated. Okay, so vertical lines. Can somebody tell me, is there any strain for the vertical lines? Do the vertical lines see any change in their length? They don't see any change in their length because the thickness has to remain the same. The only thing is the vertical lines have rotated, so there are no, they undergo zero strains in that sense. Okay. The third thing is that the horizontal lines now become curves. Horizontal fibers. They become curved, and here is something that is even more nicer. Initially, when I looked at the undeformed profile, the length of the line AA was the same as the length of BB was the same as the length of CC. Now, after the deformation has taken place, let me call them as A prime, B prime, B prime, and C prime, C prime. The length of A prime is now lesser than what it was before. These are the observations one can make from an experiment of this sort. It's a thought experiment, right? The length of A prime is lesser than A. The length of C prime is larger than CC, which means that the line segment AA has shrunk or compressed. The line segment BB has, CC has stretched or undergone an extension. If something is compressing and if something is stretching, then in between there should be a line that has not undergone either. Does this make sense to everybody? So, there is one special horizontal fiber along the length of this beam which has not undergone either a stretch or a compression, and this fiber has a special name. It's called as a neutral fiber. It does not take sides politically. You can be compressed or you can be stretched. Yes?
Does that mean it's still straight?
It is curved, but it's not stretched.
Okay.
Right. So the arc length, if you think of it, and these are all like highly exaggerated in some sense. The arc length, for example, if I assume that BB prime is the segment that was not undergoing a stretch or a compression. Its arc length will be the same as its initial length. Okay, so I'm going to write these things down. So A prime has compressed. C prime has stretched. Which means somewhere in between there is a fiber that has undergone neither a compression nor a stretch. Somewhere in between a fiber that neither stretches or compresses. And that fiber is called as a neutral fiber. And so look at this. I'm going to call this angle as d theta. Some really small angle d theta. Okay? I'm going to say that for the sake of simplicity, this curved length b prime is the same as bb. So for us, bb is the horizontal neutral fiber. Say okay, so that is our neutral fiber. I'm assuming, okay, this is just for simplicity. I know that somewhere in between the top and the bottom there is going to be a neutral fiber. Okay, so this is my neutral fiber. I'm going to say that the radius from the center of this hypothetical circle, okay, this is just an imaginary circle, all the way to where this arc b prime is, I'm going to call that as a radius rho. Okay, so that's the radius rho. From O, which is here, to the neutral fiber. Is everybody with me so far? I have this piece of the beam, I cut it off, I bend it. To imagine how the bending process takes place, I construct a thought experiment by saying that, okay, if I'm bending it in the positive sense, then I'm essentially taking that beam and wrapping it around this huge cylinder. I'm not really interested in the radius of the cylinder and so on. These are quantities that we will discard by the wayside later on. But for the time being, I'm going to call this as the radius rho. Top fibers stretch, bottom fibers in tension. Somewhere in between is a fiber with zero strain. I call that as a neutral fiber. Okay? Now, very important point. I'm going to say that the distance y, which is still the vertical distance, this is because the radius rho is very, very large. Okay, so rho is very large. So I'm going to say that from the neutral fiber, as I walk towards the center of this hypothetical circle O, that radial distance, I'm going to call it as a distance y. Okay, so y is still a radial distance, but it is hypothetically vertical. What is typically vertical? Because the radius rho is very, very large. Okay, it's almost like you're walking on Earth and then you're seeing that, okay, the Earth is flat. There are people who are idiots who believe that. But the Earth is actually a curved surface. You don't see the curve. Okay? Alright. I have to get it out of my system. y is the radial distance, but it's in fact vertical, okay, because of the scale of the radius that we're looking at. It is always going to point from the neutral fiber positive up, which means that if I'm looking at the thickness is now going to be t by 2 from the center of the neutral fiber all the way to the top and the bottom. So this distance is t by 2, and this distance is also t by 2. Right? Does this make sense to everybody? I'm sitting at the middle, halfway to the top, halfway to the bottom is t by 2 and t by 2. But according to the coordinate system that I have, if I go to the top, it's plus t by 2. If I go to the bottom, it's minus t by 2. So look at this. I'm going to complete this and then we'll take off. The length of AA is the same as the length of BB, is the same as the length of CC, and it is equal to the length of what? It is equal to the length of B prime, B prime. You all agree with me, because that's a neutral fiber. What's the arc length? Radius times the angle, so this is rho times d theta. This is before the deformation took place. After the deformation has taken place, can somebody tell me what the length of A prime is? What's the radius going to be at A prime? Yes, sir?
D theta times rho minus t over 2.
Rho minus y, rho minus t by 2 times d theta. Fantastic. So this is going to be rho minus t by 2 d theta, length of C prime. What's that going to be? Rho.
It's going to be the same thing, but just plus t plus 2.
Beautiful. You immediately recognize, hey, this fiber has reduced in length, and this fiber has increased in length. So this is undergoing a compressive strain because its length has reduced. This is going an extensional strain or a tensile strain because its length has increased. What is the strain? LAA prime, LAA by LAA is epsilon AA. If I do the calculations, you'll end up paying minus t by 2 divided by rho. Okay? I'm just taking this length, subtracting it from that length, and then dividing it by the original length. And so, last line for the day. For any general fiber that is at a distance of y from the neutral axis, y above the neutral fiber, sorry, the strain is going to be the following. Is going to be, if it's at the top of the beam or the bottom of the beam, it's plus or minus t by 2. So if it is at a distance y from the neutral fiber, the strain is going to be y by rho with a negative sign, which tells you that the strain is increasing linearly as a function of y. It's increasing from 0 at the neutral fiber, where y is equal to 0, all the way to either plus or minus t by 2 at the top and the bottom. Thank you all. See you on Monday.
Don't get me wrong, it's gonna be hard. But I like the concept. I'm interested. Dynamics and this shit. I like dynamics too, but like, it's just not enough.